Welcome to the 14th lecture in mathematical finance. Right, so let us come back to the binomial model. And as I promised you today, we want to show that the binomial model with several trading periods is indeed a complete and arbitrage-free market if the parameters are chosen in the right way. And then we can study the pricing and hedging problem of European option in this model. And the big advantage of the binomial model is that everything can be calculated explicitly, assuming we know the parameters. Okay. So let me recall the binomial model. Which we have. So formally, I set it up last time. So formally means in the mathematical rigorous way, saying, okay, this is an example of a probability space, which you can use to set up the model. But of course, there are other choices as well, right? So this is, you want to model a probabilistic experiment, and there are different ways to mathematically describe such an experiment. Okay, so we consider the one-dimensional case. As I said already last time, the multi-dimensional case is straightforward from this, and this means we have one risky asset, risk-free asset. So let's start with the risk-free one. Which starts at some t0 with the price to be 1. So we normalize the price of the risk-free asset to 1. This is our risk-free bond. And here, well, let's be optimistic. So we have an interest rate of R. So at time t1, the price moved, let's say, a bit upwards by the interest rate R over this period. And then we keep doing so. So that's right. So then at the time 2, if we invest in this risk-free asset, we have now 1 plus R to the power 2. Right, and so on. So this is the idea you have want to keep in mind. So this is the how the risk-free asset looks like, and here at some point we have our terminal time, capital T. Okay, so this is the bond in which we can always invest and make surely some losses or some gains. So here, let's assume the interest rate is positive, then we make surely some gains. Then we have the risk key asset, which is the more interesting one. So let me go, because I need to draw a tree. So let me start below here. So we at time 0 again, we have the price as 0. Right? So this is a constant. We know this is time 0 is always the moment in which we are currently, and then the price is going up, down, which is strictly speaking not necessary. So even the downward factor might be bigger than 1, so the prices could always go up. Well, I think the picture we want to have in mind is like this, the tree going up and down. And then at time 1, right, the price is either, when you move up, so 0 times u, or we go down, then it's d multiplied with the 0. Okay, and then we go to go up and down again, or we go up and down. And the reason why you want to have a recombining tree is for numerical reason, because the complexity is much lower if you assume that this tree is recombining. So what we assume is that the price at 0 might be, doesn't matter if you go the tree up and down or if you go down and up, the price is then the same at time 2. And here we are at time 2. If you go twice up, if you go twice down, you're here. Right? Now you can keep playing. Okay. So again, you might go up, down, up, down, up, down. Right. And then, well, you can keep playing this game until you reach the maturity time. So right until you are at terminal time t. So this is basically the tree describing the movements of the risky asset, and then you usually start with some physical measure. So the probability that you move up is called p, and then the probability that you move down is 1 minus p. And they are, so that's the probability. And to make our life interesting, I mean, it should be strictly positive to go, so the probability to go down or to go up should both be strictly positive. All right. So that's our tree describing the financial market. And now, so just one little definition, or which is not super important for the course here, but you might have seen it already, or it might appear in financial context in different situations. So the return of the risky asset is now, right? So this is what you get if you invest in the risky asset over the teeth trading period. And so that's ST minus the price, so the price at time t minus the price at time t minus 1 normalized to what you need to pay to get it. Then okay, here we actually know what it is. So it's u minus 1, right? So if you go up at the teeth time, if you go up, then this is u minus 1. And well, we can for a moment denote this by, let's swap the color again. So let's denote this by u hat. And if you go down, well, this is u, right? You just look at the definition of the price process. That's what you get. All right, and here we can shorten our notation again by calling this d hat. Okay, so this are the returns, and then you can easily express the price at time t in terms of this returns by saying, well, this is nothing else than the price at time t-1 multiplied with the return, which is again a random variable. This is, of course, here true for t up to t-1. And this also means that R, so the interest rate, is nothing else than the return of the risk-free asset. So this is the return. So this is R is the interest rate. So this is what you get if you invest in the risk-free asset over each period. Okay. So that's our model. And well, if you want to do any financial mathematics, the first thing we need to do is to check that it's arbitrage free. And here I also promised you that it will be complete. So let's check this as well. So that's the content of proposition 416. All right. So what's the statement? So the binomial model, as I just described it, is arbitrage free if and only if, and this is the same condition as we have seen in the one-step binomial model. So at the moment D has to be strictly less than 1 plus R, has to be strictly less than U. And we can also like formulate this in terms of returns. So this means the return that if we go downwards has to be less than the return of the interest rate. I mean, from the interest rate has to be less than the return from the upward move. Let me put our usual condition here. So here, right, R is a constant being bigger than 1. And let's put it here. U, D have to, I mean, they're ordered and they should be non-negative, right? You want to have positive prices. Okay, so what does it mean here? I mean, this is not part of the statement of the theorem, so let me make here a little box to draw a picture for you. So what's a nice color for this? Yeah. So if we are, so what does this arbitrage free condition means? Means, well, if we invest in the risk-free, so if we, in the risky asset, right, we start here at, so this is the movement. So this is S0 and this is S1. So this is DU. So this is the price at time 1. Right. And the arbitrage free condition tells us now, well, If we invest in the risky asset, this should be, I mean, give us like either higher or less returns than if we invest in the risky account, right? So somewhere in between should be okay. So because if we invest in the risk-free asset, we have a certain return. So this is, we get surely this amount of money, and to keep the market arbitrage free, oh, of course, right? This should be not better than the risky asset, and this should be not worse than the risky asset. Right? So these they should be comparable. Okay, let's come back to the statement because so if we have now an arbitrage-free binomial model, in this case the model is also complete. So every claim is replicable, as we have seen in the binomial model, in the one binomial model with one trading period. And what else I am? And the unique equivalent Martingale measure Q is, well, so that's right, these Y where the random variables modeling the upward and downward factor at the Tth trading period. So this is what we always called Q, and Q, as we already derived, should be this. Right. Or equivalently, can formulate this also in the with respect to the returns of the risky asset, right? So the probability that the return is d hat, so one by u minus one, then this is again q, and well, we can also like rewrite this as, this is just plugging in the definitions of u hat and d hat. Okay. So here, so we characterize first that the market is unique, it's arbitrage free, and the Martingale measure is unique, as we will see in a minute. So the market is complete as well. All right, so that's what we need to prove now. And now the advantage compared to what we have seen in the one-step model, binomial model, is, well, now we have the nice abstract theory which tells you what we need to do. So to show these two statements, I mean, it's much simpler. Proof. Okay, let us, right? So Q is a Martingale measure. Right, so if I want to have something, some object to be a Martingale measure, then this means, well, by definition, the discounted price process is Q Martingale, so Martingale under Q. And that's equivalent to say, well, look at the discounted price part, the discounted price process. It needs to have the Martingale property under Q. Yeah. Right. And what is this? Right, we can express this, well, as the price at time t, and this is ft measurable, so we can pull it out of the conditional expectation and then multiply it with y at time t1 divided by the discounting factor, which is 1 plus r. And this holds for t equal 1 to t minus 1. Right? So this is just recalling what it means for measure Q to be a equivalent Martingale measure. And we want to have an equivalent Martingale measures because we know by the first fundamental theorem, asset pricing, a market is arbitrage free if and only if there exists such a equivalent Martingale measure. All right. Okay. So what does this mean? Or the last equality means, okay, I can divide both sides by as the discounted price at time t. So I get here, and let me move over the ARP plus 1. So this is the other side now. Has to be equal to the conditional expectation of y t plus 1 conditioned on ft. Okay. And now we know that the y is independent of ft. Right? T plus 1 is independent of ft. No. Okay. And well, what is this? And this is a random variable which can take only two values. So it takes either the value u with the probability that is t plus 1 missing, plus 1 is equal to u. And it takes the value d with the probability that this is equal to d. And now, okay, since this is a probability measure, I can re-express this as 1 minus the probability that y at time t plus 1 is equal to u. Okay. So let us rearrange this in order to get the probability of under Q that y t plus 1 is equal u, or this is nothing else than 1 plus r minus d divided by ud. And this has to hold for all t from 0 to t minus 1. And next thing we need to know is here. So if we can find a Martingale measure, then it's uniquely determined by this equality 4.3. So determine. So if there is a Martingale measure, we know it's unique, and this means the market is complete by the second fundamental theorem of asset pricing. Okay, so now we just need to ensure that there exists such a. So if there exists Q, B, S, T is complete. This is second fundamental theorem of asset pricing. Yeah. All right. All right. So let's see whether there exists such a equivalent Martingale measure. So when we have derived a quantity here, how Q should look like, but we need, by the first fundamental theorem, asset pricing, need an equivalent Martingale measure. Right. This is not. Well, that now, right. So what does it mean? So we considered just some measure. Okay, and that's what we basically did it. That it has to be a probability measure, but it does not mean that it has to be complete. Sorry, that it's equivalent. So in order to ensure that it's equivalent, we need to ensure that the probability of under Q that yt plus 1 taking the value u, which we recall was 1 plus r minus d divided by u minus d, needs to be strictly between 0 and 1. Yeah? Because all events have to have a strictly positive probability. Okay. So, and well, if I have this here, this means my d has to be less than 1 plus r. This has to be less than u. All right, and this is exactly the claim I made here for the binomial model to be arbitrage free. And this is all equivalent here. So we indeed have we verified that if the market is arbitrage free, then this condition has to hold. It's better formula in there. All right. Okay, how do we get now? I mean, that the market is arbitrage free. Well, we have the assumption that this relation between the parameters holds. And now we use our condition of equality we derive 4.3, which is here. You can see still here. So we define equivalent Martingale measure Q by and so the probability of an omega in omega is given by what Q. So T minus K if this is over. So we have here, so if you call our probability space, our omega is a vector consisting of T entrants. And we assign it to this probability if it contains K times an upwards move. Yeah. Right, so Q should be the probability that the price moves upwards. And so this means if you have a scenario, if an event, scenario appears on the market, which is omega, which has k times an up movement and t minus k times a downward movement, then this is the probability where Q is our unique choice we have for the Martingale measure. So that's the definition, right? So hence Q is equivalent Martingale measure by the calculation we just have done. And this means is arbitrage free by the first fundamental theorem of asset pricing. Okay, here we are. Okay. So let us now come to the pricing and hedging problem. So of course, so what we need to do to give this make sense of pricing. So we assume now that our binomial model is arbitrage free, right? Because this is then the realistic model for a financial market. And now consider the pricing and hedging problem of an European option. So a European option is, well, if you recall from the abstract theory, is just a non-negative random variable, which is FT measurable. And if you think about the simple probability space, I mean, what are our FT measurable random variable? Well, they are just functions. So we take a measurable function, measurable function f mapping from our plus, right? So our prices are positive to our plus. So we want to have a positive payoff or a non-negative payoff. And we plug in our T+1 prices, so the prices we observe in the market. So these are our options. Okay. Right. So how do we approach this problem? So first thing, what we know is exists a unique equivalent Martingale measure. So this is equivalent Martingale measure Q. So we have this Martingale measure, and now since we have here a complete market, we know that the value process or the price process of the option psi is given by well, the discounted, so you have this discounting factor and then you take your option. right? So this is, if you want to check it out again, so that's with the content of lemma for 6. Okay. So, and now the good thing here is, okay, let's keep here the vector is, we are here in on a finite probability space with a very simple, simplistic model, the binomial model, so we can calculate this conditional expectation explicitly. Right, the first thing is what you observe here. Well, let me rewrite this as, well, there are the part which you observe. So if you're at time t, if you want to know the price at time t, we can use the information up to time t. So we have here, we keep this one, and then, well, the prices coming afterwards, we express them in a measurable part, which is the price at t, and an independent part, which is this, right? And now we realize, well, that, well, we have the measurable that's actually no, wait. Right. So let me give you the first part of proposition 4.17, which tells you, well, the price process, you see here, this is the price process, is given by t psi. So we have here our discounting factor, and this is just the function depending on time and the prices up to time t. Right? Because this is, I mean, you see here, the price has to be ft measurable, so it can only depend on the information up to time t. And we know actually that ft, we plug in the prices up to time t, so these are just constant now. This is nothing else than 1 plus r, so we calculate here the discounting factor. So the definition of b is plugged in, and then we have, right, so these are the known prices up to time t, and then we have t, and then 1 minus t up to time t, t minus t. So they're independent, so we can forget the filtration up to time t. Okay, so this is so t in rt plus 1. Right. So this is just plugging in. We know this leads here. Okay. And now, okay, and this is still a expectation. So in principle, okay, you know how to calculate this expectation, because you know the measure Q, and well, you know all the distributions of all random variables, so you can explicitly calculate this conditional expectation here, or here just an expectation, and you but let me give you also like a even more simpler recursion theory formula. So recall, so if you look at the discounted price process, right, by the definition of an arbitrage-free price, this is a martingale. So this means this is nothing else than t plus 1, like dp plus 1 dt, right? Since so the discounted price process is a Q martingale. This was the idea of an arbitrage-free price, that the Q is also martingale measure for the enlarged financial market where this option is traded, right? So when you see, you can express the value process at time t in terms of a conditional expectation of the value process at time t plus 1. Okay. Which color? I use green, sorry. Okay. So this brings us to the next part of our proposition 4.17. Well, so if I look at my value function, v, right? This is this little v we just defined here. So what do we know for the value function? The value function at, or the price function at time, terminal time, has to match the payoff, right? And then at time t, if I plug in the prices up to time t, so what has to be the value process? Well, we have here our discounting factor, right? This is coming from these two discounting factors, -1. And then, so the value function at time t is nothing else than the conditional expectation of the value function at time t plus 1. So we have here t minus u plus 1 minus q, and then the value function for the downward move. T downward, right? For what is it? T up to time t minus 1, and x again the prices of time t. Actually, I should write pluses here. No. All right. So again, I mean, this is just taking this abstract formula and calculating it explicitly. All right. And now, yeah. You know, I mean, this is a complete market, so you also have an replicating trading strategy. So the trading strategy phi beta t. So this is, well, risky asset, risk-free asset, is given by, well, so again, this is, it's a function, so that it's a predictable function. So this is depends only on the price at time t, on the price at t minus x, and this is defined as, well, so what you want to do is you want to hedge the movement of the value function from time in the t trading period. So right, you add time t minus 1, and you want to hedge what the payoff at time t. So this is a simple linear system which we have solved in the 1 step, and now we just abstractly solve it for each knot in the tree. And what you get is this. Xt minus 1. Right. And this is 3. Right. So if you scroll again up a bit to this formula here, that you just need to think how to replicate this, the movement from time t to time t minus, from time t to, sorry, t minus 1 to time t. And this is, I mean, this is what often is called delta hedging, and right, this is nothing else than a discrete derivative. And this is the derivative in the mathematical sense, right, of the value function. And so you can use yourself again to write this out explicitly. Regarding, so I think it's rather clear what to do. But if you want to check out some more details, you can look at the lecture notes. Regarding the proof. Right. All right. One little formula which you can derive from this general theorem is, well, corollary 4.19 is, well, if we have an even simpler function like a put or call option, so let xi be a claim, and now I think of a put and a call option, so it's a claim which only depends on the price at the terminal time. And then the price here of chi is, well, you have your discounting factor. And then you calculate the, right? So you go up here, look at our pricing formula, right? So this is here the pricing formula we want to use. So we have here the expectation if we want to look at the price at time 0. So we just have the expectation under Q of the discounted payoff, right? And our payoff now only depends on the terminal price. So let me give you one step more. So this is correct, but me. So this is 1 over T of the expectation of this claim under the measure Q, right? And now we have here our tree in mind. So what is this expectation here under Q? Well, what do we have? Well, we have the probability. So we have finite number of values on which these random variable can pick. So we know the payoff can be only f applied to f0, and then depending on how much time we moved upwards and how many time we moved downwards, right? So let's say we moved upwards t times, and then we move downwards t, capital T minus little t times downwards. The probability that this happens, or one tree is 1 minus, right? And the number of path how I can reach this value is capital T over T, right? So here we are, that's it. So if you have a binomial model, you want to price a European call or put options, and you take your parameters, so you calculate your risk neutral measure or the Martingale measure Q, and then you plug it in your computer, which spits out this expectation. Okay. So I think that the main message is in the binomial model, we can compute everything. Okay, this is of course wake statement explicitly. Right, so this is nice because then we can numerically approximate even more complicated situation that we see in the probably last week of this term. You can approximate complex models with these rather simple looking binomial models if you assume the right scaling for the parameters. So this is super helpful, this is super useful, and I believe you are able to do the calculations here on your own. Yeah. And this means also all the exotic options, I mean, you can derive rather explicit formulas for the prices. Okay. 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 I think we understood now the pricing and hedging problem for European options rather well. But at the beginning, we also discussed some different types of options with different exercise rights, and the main other examples are American options. So let us come now to our next chapter, which are American options. Okay. There was the difference between American and European options. So European options, you buy and you have the right to exercise it at the maturity time, which was always capital T in our case. And now we had also this different type of exercise right created by the American option, which where you could exercise the option at any time before maturity T. So, yeah, but also including maturity T. So American option. So an American option. American option can be exercised at any time before maturity. So it's not a strict before, it's including maturity time T. And the maturity is for us always the terminal time of our model, so capital T. And these additional exercise rights make it, the pricing and hatching more complicated compared to the same problem for European ones, because there's a asymmetry between the buyer or holder of the option and the seller of the option. Because the seller sells the option and then he has no influence anymore when the buyer will exercise it. So this is somehow, there's a game component associated to this option. Okay, so we leave now the world of the binomial model, but if you want to, you basically can keep it in mind, well, the binomial model as the standard example. So what we want to assume is we consider here finite, so this is to make our life easier, one-dimensional arbitrage-free model. Financial market, as usually denoted by B and S, and as usual, right, so this is, it's just saying, I mean, so this B and S, and there will be in correspond to general risk-free asset, and well, we normalize the time time t equal to 1. Right, so this is, and secondly, we have our risky asset, which is now again a general stochastic process, and not necessarily a binomial model, but okay, it's one dimension, so we have one risky asset. Filtration is usually given, well, generated by this risky asset here, not by the price process of the risky asset. Okay. So what's now the difference to European one? Where the first difference is where we had these additional exercise rights. So meaning the holder of the option can exercise at any time before maturity. And so we need mathematically to define as a first step what is the payoff of the option of any time before maturity, right? So the definition. So first thing, we want mathematically define what an American option is. And these definitions, again, motivated or verified economically by our no arbitrage principles. Okay. So what is an American option? American option. Or American contingent claim is a non-negative adapted process. So C equal to, right? So the non-negativity assumption here again corresponds to the idea that the holder will not exercise the option if you would lose money, right? So why should you exercise it? Right, so this is American option. And adapted, well, this is the idea where, okay, the option depends only, the payoff is determined. So the payoff at time t is determined by the prices up to time t. Okay. And as before, right, we have also the discounted one. Discounted American option is, well, if we discount this one by our risk-free one. Okay. Right, so that's t equal t. So the usually idea, if I write a tilde, is the discounted counterpart of the undiscounted option or process. Okay. So let me give you some examples. So standard examples we want to keep in mind are American put and call options. So the American put option. So denoted by C put. Right, so it's an American option C, put for put option. So that's has to be a non-negative adapted process. So here we are. And well, for put option, we also need to say what the strike price is for which we can buy the option. So we have the strike price K And the payoff at time t of this put option is, unsurprisingly, so we're talking about put, so you can sell the option for the strike price, for the strike price k. And this is k minus st. And you only do it if it's, if you make no losses. So you sell if you exercise. This is the payoff if you exercise it, the option at time t. Right. So this is an numeric put option. Okay. And now what is the American call option? C call. Again, process, call, which is non-negative and adapted, is given by, so C call. So you have a call option which you can exercise at any time. So, if you exercise at time t, the payoff is st minus k, and then you only the positive part, because you will only do it if it's, you make no losses. All right. So these are these two most common examples. Again, European options, American call and put options. Okay. Okay. Right. And now, what we defined this type of option with a as a adapted heuristic process, because the buyer has the right to exercise at any time. So we need also to mathematically model this idea of the buyer exercising the option. And well, the mathematical way to do so, because the idea is how a buyer can exercise, of course, is he or she should only use the information available up to time t. And this brings us back to stopping times, right? So let us briefly recall what a stopping time was. So I have a random variable, omega, tau, mapping from omega, so our sample space, to the index set and infinity, right? So I have a random variable taking values in our index set t, or taking the value infinity, is called stopping time. Well, we can decide at time t whether we want to exercise or not, or whether we want to stop or not. And this is what expressed in terms of our filtration. So we can decide whether we know that the event that tau is less or equal than t is ft measurable. So for t in t, right? This is doable for all the possible times. Okay. And now let us come to the definition of an exercise strategy for the buyer. This is definition 5.3. So how do we allow the buyer to exercise an option? Well, nice strategy. How? For an American option Okay, so you should see. Is stopping time with values in t. So g tau less or equal than t. So what we want to do is we say, okay, the right notion of an exercise strategy are stopping times, and the only feature we want to add here is that we assume that this stopping time takes always only finite values. And this is just to make our life mathematically easier, right? Okay, now you can argue, but why can we do this? Because in principle, the buyer, does not need to exercise the option. There's no obligation to exercise the option, but this is, no restriction here because we already put the assumption that the payoff is non-negative, right? So the terminal time you can always exercise and you make no losses. So the idea of not exercising is actually included in our modeling by saying that the payoff is non-negative. So we can make it this additional assumption that the stopping time is less than t, and still keep the idea that the buyer is not obligated to exercise the option. Yeah. So that's no, restriction or so. All right. Okay, and now, okay, we have this option. So we want to understand what is the price, right? First, as for the European option, we first think about, okay, what's the right price if we start trading it on the market? And then we think about, okay, if we are the seller of the option, how can we hedge ourselves against the risk of having sold this option? So again, we call a bit of okay. So if I have a European option, this capital pi of psi, it's the set of arbitrage-free prices. Of the European option. Exactly. Right. And now I want to define what I mean by an arbitrage-free price for an American option. Definition. 5.4. Okay. Again, well, a real number. So the price at time 0. So we focus on the price at time 0. So the price of an American option, let's call it PA to distinguish it between American and European ones. So C as an American option is called arbitrage. Arbitrage-free price of the American option, C, right? And to remind you, C is a process which is non-negative and adapted if, and now we have two conditions. First one, they exist. The stopping time tau. Okay, so this tau should be an exercise strategy. So there exists an exercise strategy, and corresponding arbitrage-free price. So that's small pi. So to the now European option C. So we stop the American option at time tau. So this is a non-negative FT measurable random variable. So in our sense, it's a European option, and we know we have a set of arbitrage-free prices. Aside to that, the price of the American option is less or equal than pi. So what does it tell us? This tells us, okay, if I'm the buyer of the option, I'm willing to pay this price, APAC, so the price for the American option, because I can't find an exercise strategy which tells me, okay, the payoff I get, it's worth the money for me, which I spent to get the American option. So I can't find the stopping time or exercise strategy which tells me, okay, I'm willing to pay this price. So the price is not too expensive for the buyer. And then we say that X is no stopping time. So again, no exercise strategy tau prime such that the price of the American option is strictly less than T prime for all T prime in the set of arbitrage-free prices of C prime. Right? So this is telling us that the price is not too cheap from the perspective of the seller of the option, right? So if I sell the option, the buyer is not able to find an exercise strategy which really gives him some positive payoff, in the sense if he buys the option for this price, then under all Martingale measures, the price of this European option is strictly higher than the price of the American one. So that's okay. Let me this here. And so let me also write down the remarks so that this because this is a definition we will work with at least for the whole next week. So I actually gave this numbers. Okay. So be consistent with the lecture notes. So right. Okay. I says the American option is not too expensive from the buyer's perspective, right? So just what I said already. So I'm willing to, so as a buyer, I'm willing to pay this price PAC because I can find a way to stop this option, which tells me, okay, they created European payoff, then well, it's worth the money. And the second one is selling, okay, and the buyer cannot outperform the seller. So the American sentence, American option is not too cheap from the seller's perspective. So here, the definition of arbitrage-free prices already, I mean, reflects this asymmetry between the buyer and the seller, right? So, because the seller can decide, the buyer can decide when to exercise the option, but the seller has no influence on this whatsoever. Okay. Right. So, so you see here, if I'm the buyer of the option, I mean, this leads me to like an optimal stopping problem or optimal exercising problem. So I have the American option, and now I want to basically optimally for myself decide when I want to exercise the option. So let me give you what the price of an American option is. And we want to do it first in a complete market, as we started within to understand the pricing in the European option and the binomial model. So the complete case, we start here also with the complete case. So if we assume that the finite market is arbitrage free, right? This is the minimal assumption we need to talk about pricing of option. So we have arbitrage free market, and we want additionally assume that's also a complete market. And then there exists actually a unique price, and this arbitrage free price, how do you call it? The American option C is process is AC is given by, okay, let me make it a bit. So and the price should somehow reflect this optimal stopping problem we face. And indeed it does. So we can represent the price of the American option as an optimal stopping problem. So we look for the stopping time tau, and we assume that tau is less than t. And we want to maximize the value of the discounted European claims, corresponding European claims, right? So this is the maximal price of all the associated European option, which I can create by stopping the American one. Just to keep it in mind, so as usual, Q is the unique equivalent Martingale measure. Right. Okay. Okay. This is the goal for next week. In order to prove this theorem, so to understand that this is the arbitrage-free price of the American option C, and also to find actually what is the optimal way to stop an American option, we need to understand this stopping problem better. Or I mean, we'll start understanding this optimal stopping problem. So we want to also to find the optimal stopping time for the buyer. And in order to do so, wait, prove later. So we will prove the theorem, but we need first to understand first and Martingales and optimal stopping better. Yeah. So this is so what we do now is we study in a general context the optimal stopping problems and martingales, or how martingale behaves under stopping. And this brings us to the next subsection, which are dupes. Theorems about martingales. All right. So okay, we're almost done. So let me just briefly set up the settings. So now we fix a general probability space, and we want that it's a filtered probability space. So this is, I mean, this not necessarily finite space. So actually, the finiteness of the underlying space is only needed for the fundamental theory asset pricings. So as we don't need them here, let's work with the general space, and well, our index set as usual, right? This is and if we can directly start with dupe theorems next time, let me recall the notion of probability of martingale, sub-martingale, super-martingale now, and then, well, next time, so next lecture, you should have these definitions like ready in your mind so that we can directly start working with them. Integrable will adapt it process, and now this is general process X in T is called, this is our usually 3. So we have a martingale if the conditional expectation of X given XT given S is XT. We have a sub-martingale if or the moves are again in favor of us. So this is bigger, and we have super martingale. If this conditional expectation of x t given s f, the filtration at time s is less, right? And this holds for all s t in t. Right. So this is what we the notion. I mean, the different notion of fair and unfair games we had. So this is martingales, and next time we start with investigating the behavior of these martingales, sub and super martingales under stopping times. All right, thank you very much for watching the video, and hopefully you stay motivated and do the exercises.